This improper integral problem has a couple issues here, and we usually won't mix them, but we're just going to do all of them at once in this problem. We have this issue of integrating across an asymptote. Okay, we cannot integrate across asymptotes. So when we do this, we have to have a limit. When we integrate across the asymptotes, we have the yellow integral here. This is approaching 1 from the positive side. Oops, sorry, got that backwards. This is from the negative side. Okay, and this is going to be approaching and then we also have the green integral, which approaches 1 from the positive side. So we need to state a limit. We need to set a limit, we can't just put 1 into our integral because it is an undefined value. So we're going to approach 1, we're going to approach h equals 1 from the negative side. So we can integrate that yellow area from 0 to h, which is 1. And then for the green area, we're going to approach 1 from the positive side, so we need a limit again. So basically, we're going to integrate from 1 to some arbitrary point A. Now that A could be anywhere, and you can actually put a number in there and do it separately if you like, but in the end, this integral goes all the way to infinity. Okay, so we do need a limit because it is bumped up against that asymptote at 1, but we're also integrating it to infinity. So I have this pink part which goes out to infinity. So notice I integrate from that arbitrary point A to h, where h is going to infinity. So this pink part here is integrating to infinity. Now we can't do this at the same time because we need a separate limit for the approaching 1 from the positive side, and we need a separate limit approaching infinity. Okay, but in the end, those two together will give us one area. Okay, so integrating these three parts. So the yellow part we can do independently. This is going to give me the yellow area. So I anti-differentiate this function. So this is a x minus 1 to the power negative 1/3. So we increase the power by 1 to get 2/3, and then divide by the reciprocal of, or divide by 2/3, which gives me 3/2. And then I still am using a limit because I can't actually use 1. So I'm going to use a limit to approach 1. And I can actually evaluate this integral. Okay, so this is now going to look like this. So I'm going to plug h equals 1 into this expression. So I get 3, and this is going to be 1 minus 1, so 2/3 over 2. So I need to give myself a little bit more room to work here. So that's going to be that there. Then I'm going to subtract. So minus, I'm going to plug in 0 into this expression. So I'm going to get 3, 0 minus 1 to the 2/3 over 2. And so working this out, this becomes 0 minus negative 1 to 2/3 is positive 1. And then that becomes minus 3/2. So this area is negative 3/2. So this represents this yellow area in here. So that's going to be an area of 1.5, and it's negative because it's below the x-axis. Now, I could choose some arbitrary point A and integrate integrate these two parts separately. Okay, but really, I should really just integrate this the way it is. And if you know your relative areas, you know that this is going to be an infinite area. So as integrating from basically A to infinity, that pink area is actually infinite because the degree on this is less than 1. Okay, that indicates that it does not converge fast enough. So this would be infinite. So we could just plug it in here, and we can actually show that this pink limit is actually just infinite. So looking at this as just this pink piece here, so I'm just going to do it in a pink color. If I do plus limit as h approaches infinity, actually I'm just going to plug it in, actually work it out. So this works out to be 3 over 2, and I'm going to plug infinity into here, minus 1 to the power 2/3, okay, minus, this is going to be some arbitrary point, 3 over 2, a minus 1 to the 2/3. No matter what a is, this is a finite value. This is finite, okay? This is an infinite value. So this integral, that area, that pink area, is going to be infinite, okay? And we can just say that that's the case, and we can also do, and so we know that together they must be infinite. We can also just figure this part out as well, the green part. And if we keep this expression in here, this is going to work out to be plus 3 over 2, and I'm going to plug in my a value here, so I end up with a minus 1 to 2 over 3. Okay, so we end up having 0 pairs here. These actually will cancel out. This is a finite value that cancels out. Okay, and so if we actually just integrated it without the a value in there, we would end up with the same thing. Okay, so formally we really need to put that a value in there, but realistically we don't really need that in there because they're going to cancel out anyways, and we would have actually ended up doing this as infinity, this infinity here, so I'll just circle what I'm talking about. We would end up with this minus this finite, this value of 0. Okay, this is equal to 0. And that would be avoiding that a value, but technically we can't actually do, we shouldn't do that, because that a value actually allows us to split this up into two parts, allowing us to use the limit for both the vertical asymptote and going out to infinity. Okay, so in the end, we end up with some finite value here. This is some finite value plus negative 3 over 2, and this finite value over here that we're going to subtract, this is actually the exact same finite value. So if we actually just ignored the a, we would end up with that area under the curve, the green and pink area ends up being infinite. Okay, so summarizing this ends up being the area is negative 3 over 2 plus infinity, so this area is infinite.